We are going to be talking about Thevenin and Norton equivalent circuits today, specifically for the cases where circuits have dependent sources included. So let's call this Thevenin and Norton. Equivalent circuits 2. All right. So I am just going to make up a circuit here. Might turn out to bite me in the butt. It'll be what it'll be. This will be something fairly straightforward. Here's terminal A, here's terminal B, and let's make this current here to be the current IX that's controlling our dependent source. Okay. So if we wanted to find the Thevenin and Norton equivalent circuit with respect to terminals A and B, what would we do? Okay. So let's first find the Thevenin voltage. Okay. If I wanted to find the Thevenin voltage for this circuit, what would I need to do?
Between A and B for the positive terminal would be gate.
Okay. So I can agree with that. We're just going to assume here positive polarity on top because I didn't specify it. No problem there whatsoever. So our Thevenin voltage would be the voltage drop across that open circuited set of terminals because we're finding the Thevenin equivalent circuit with respect to a set of terminals as opposed to with respect to a particular circuit element. All right. So how might we go about finding that voltage in particular? So I'm going to assume that you said that just to piss me off, which is fair. Here's why I wouldn't use mesh analysis. There's only one mesh. Right? The right-hand thing is open circuited, which means it's not a mesh because there's no current flowing through it. So you can't even really do mesh analysis even if you wanted to. Good try though. So could we do voltage division to figure out what IX is? Okay, so you then modified your statement to say that if we found the voltage drop across the 8-ohm resistor, we could find IX. I believe fundamentally that we should go in the opposite direction. And the reason why I say that is because I truly believe that if we look at this circuit hard enough, we can see what IX is without doing any work whatsoever. So why do I believe that? Troy? Nope. No, you guys are just, not to be a jerk, completely and utterly dropping the ball here. You're laughing? Why are you laughing? Is that me being a jerk or? Okay. Let me ask you guys a very fundamental question here. Is the 8 ohm resistor part of a closed current carrying loop? No. So how much current flows through a resistor that isn't part of a closed current carrying loop? 0, right? It does. So by inspection, IX must be 0. No current can flow through the open circuit. That means also that the current for IX flowing down is also 0, which means that current source, that dependent current source in the middle of the circuit is behaving as if it were an open circuit because it's carrying a current of 0 amps.
It doesn't become just a wire. It doesn't.
Yes. So if this current is 0 amps and this current is 0 amps, what's the current flowing through the 10 ohm resistor? It has to be 0 amps. So taking all of these 0 currents into account, what is V Thevenin? Do Kirchhoff's voltage law around this loop. Positive 30 volts. So you guys tried to throw just tons of stuff at this problem where literally settling down for a moment and just looking at it would have gotten you a lot farther than throwing every analysis technique you can think of at the wall and seeing what sticks. I have the battery in my hand. Does it still have the voltage drop across the terminal of the battery? Yeah. So, any questions about how we found VTH here? By the way, this or something extremely like it was a question that I asked on an exam too in the past couple of years. All right, so finding I Norton. How do we find the Norton current? Short circuit our terminals. And the Norton current is specifically the current flowing through the short circuit. Okay. So it should be fairly obvious then that IX and I Norton represent the same current for this particular problem. Okay. So how would we solve for that current I Norton? So we can't start from the jump and say it's 0 because we do have a closed loop. Yeah. It could be 0, but we can't. Fair. So in order for us to do current division, we need a known amount of current passing through a network of resistances that are in parallel. We don't have a known amount of current, nor do we have resistors in parallel. So could we do a source transformation? Absolutely. That would put our resistors in parallel, but then we'd still have the issue of not really having a known amount of current because there is, we're still gonna have that current source of 4IX pushing down, which is an unknown quantity. So I don't know how much that's gonna help. Now we do mesh. We have eliminated all of the other possibilities effectively. Now we do mesh. So let's call this mesh current I1. This mesh current I2. Sorry, I'm so used to using complex numbers. I'm putting bars over things that don't need them. So how am I going to apply mesh analysis to this circuit? I'm not saying that you're incorrect, but you're definitely not doing it in the order that I try to get you guys to do it in. So we have a controlling variable, right? How do I express my controlling variable in terms of my mesh currents? Okay. I have a current source, which means I have a current relationship equation. What's that current relationship equation going to look like? And then we do the KVL around the outside loop. Yes. So I ask you guys to do it in the order of controlling variable relationships and then current relationships and then the KVL relationships, because it's easiest to forget to do the defining your controlling variable and then defining your current sources in terms of your mesh currents. When you're doing mesh analysis, the meat and potatoes part of it is the Kirchhoff's voltage law equations. But I get asked so many questions of like, I was only able to come up with 3 equations. Where's my last one or whatever? It's always one of those 2 things. So I ask you to do them first so that you just get them out of the way. So doing KVL around the outside loop, because we have a super mesh, we're going to have negative 30 volts plus 10 ohms times I1 plus 8 ohms times I2 is equal to 0. And then we are going to solve this system for, I'm going to be just really lazy and solve it for I1, I2, and IX. We could very easily make this a 2 equation, 2 unknown system by doing substitutions, but I don't want to do algebra right now, so I'm not going to. So we have 3 expressions or 3 equations here. So the coefficient for I1 in my first equation is 0. The coefficient for I2 in my first equation is 1. The coefficient for IX in my first equation is going to be -1. When I move IX to the same side as the variables, my constant term is 0. In my second equation, my coefficient for I1 is +1. My coefficient for I2 is -1. My coefficient for IX is -4. And my constant term would be 0. In my third equation, my coefficient for I1 is 10, my coefficient for I2 is 8, my coefficient for IX is 0, and my constant term is +30. Solving this system, I get I1 to be 75 over 29 amps, I2 to be 15 over 29 amps, and IX to also be 15 over 29 amps. And IX is I2 is I Norton by inspection. All right, so we found our Thevenin voltage. We found our Norton current. Now let's talk about finding our Thevenin resistance. Okay. So the short answer to that question of can we just Ohm's law as a verb, which I find interesting, is yes, right? So by definition, the Thevenin resistance will always be the ratio of the Thevenin voltage to the Norton current. So that would be 30 volts divided by 15/29 amps. Or 58 ohms. Now, to ask you guys a different question, or the same question in a different way. What if we wanted to find the Thevenin resistance by looking at the circuit? How do we find Thevenin resistance using circuit analysis techniques? We have to look at a dead network, which means I'm going to have to do what? So turn off all independent sources. In this case, our only independent source is a voltage source. We turn off a voltage source by short circuiting it. Okay. And then we would look in through these terminals to find REQ. So let me ask you guys a question. How the heck do I get 58 ohms looking into that thing if I only have a 10 ohm resistor and an 8 ohm resistor? The dependent source is what's messing things up, and it's what's preventing us from directly using resistor combination techniques in order to determine what that Thevenin resistance will be. So what we're going to have to do is we're going to have to use Ohm's law. But really, it's the Ohm's law that we experimentally determined on the second day of class, right? And so what I mean by that is we are going to apply a test source. Okay. We are going to measure the voltage drop across the test source and the current flowing out of the test source, and our Thevenin resistance will be the ratio of our test voltage divided by our test current. Because if I have literally any two-terminal electrical network, and I can measure the voltage drop across the terminals of the network and the current flowing through the terminals of the network, I know the resistance of the network. Now, I have intentionally not drawn whether this is a voltage source or a current source, because realistically, we could use either, right? So if we're going to apply the test source method, we are going to choose whether or not we apply a voltage source or a current source. We get to choose the polarity of the voltage source, we get to choose the direction of the current source, and we get to choose the magnitude of either of them, okay? So we are going to work this once with a test voltage source and again with a test current source, and show that regardless of which test source method we use, we're going to wind up getting the exact same result. Okay. So let's start with a test voltage source. Okay. So let me short out this guy again. And we're going to apply a voltage source here. Do we want the positive polarity terminal to be on top or the positive polarity terminal to be on bottom? And I'm asking that. It is entirely an arbitrary decision. Does not matter which one we choose. Positive polarity on top. Okay. What magnitude do we want to use? Also, literally does not matter. 1. Okay. That's typically how I do it as well. Just a 1 volt voltage source or a 1 amp current source. Unless I have kilo ohm resistors, and then I might use a milliamp source just so I don't get ridiculously large numbers. Yeah. So what we've done by choosing to apply a 1-volt source is we have defined V test to be exactly equal to 1 volt. So we don't have to find that anymore. We set it to that. Now we simply find the value of I test, divide 1 volt by I test, and our answer should be 58 ohms if we've done things correctly. So how would we best go about determining quantity I test? Yeah, mesh is a perfectly reasonable thing to do here. Absolutely. So here are our 2 mesh currents, and we can see that I test is just negative I2. So starting with our controlling variable relationship, we have Ix is equal to I2. Our current source relationship, we have 4Ix is equal to I1 minus I2. And then when we write our KVL equation around this super mesh, we are going to have 10 ohms times I1 plus 8 ohms times I2 plus 1 volt is equal to 0. And we'll solve this system of equations for I1, I2, and Ix. So 3 equation, 3 unknown system. For my first equation, my coefficient for I1 is 0. My coefficient for I2 is 1. My coefficient for Ix is -1. My constant term is 0. In my second equation, my coefficient for I1 is 1. My coefficient for I2 is -1. My coefficient for Ix is -4. My constant term is 0. In my third equation, my coefficient for I1 is 10. My coefficient for I2 is 8. My coefficient for Ix is 0. My constant term is -1. Solving this system, I get -5/58 amps for I1, -1/58 amps for I2, and -1/58 amps for Ix. We know that I Norton is simply negative, excuse me, not I Norton, I test, my apologies, is negative I2, which would be positive 1/58 amps. Sorry, the amp should go in the middle there. And from this, our Thevenin resistance is going to be V test over I test, which is 1 volt over 1/58 amps. Very obviously comes out to be 58 ohms. So we got the exact same result. That's great. Now, actually, does anybody have any questions about the analysis that we did there? We are going to now apply a test current source. So what value, actually, what direction of current do we want to choose? Up or down? Up. So I agree with that reasoning. So I'm going to choose to do the current down so that it's in the same direction as Ix, so that whatever we choose is literally just Ix. Okay. Oh, I need to short circuit this voltage source. Sorry about that. What value do we want to choose for our test current? 1 amp, sure. Seems reasonable. Okay. Yes. So 0 would be an open circuit, which means we're not applying, like we have to have some sort of test signal to use. So it can be literally any value but 0. Because if we choose 0, we're not exciting the circuit and seeing what the response we have. Okay. I'm going to define my test voltage as follows. Yeah, absolutely. So how are we going to go about solving for the quantity V test here? So I personally feel like this is a great place for us to apply Kirchhoff's current law and then Kirchhoff's voltage law, okay? So what I mean by that specifically is we know that the current flowing into this node is 1 amp. We know the current flowing here is 4 amps because we chose what Ix was, right? So what would our current here be? 5 amps. All right. So what's the voltage drop across our 10 ohm resistor? What's the voltage drop across our 8 ohm resistor? So what's V test? So we have 50 plus 8 minus V test is equal to 0, which means V test is 50 plus 8 or 58, right? And we got the exact same result as before. Which of these two methods was easier? In this particular case, I believe that choosing a test current made the analysis a little bit easier. Now, it won't always be true that using a current source is easier than using a voltage source. It just depends on the circuit. The reason why a current source made this analysis easier, in my opinion, was because we got to control or we got to decide what the value of the controlling variable was for this dependent source problem, right? If Ix had been defined as this current, we wouldn't have been able to make that decision. And so probably a test voltage source and a test current source would have been the same level of complexity. So you can realistically have a better option to solve the circuit with, but either one of them absolutely works. Okay, so you can't do it wrong. You can just do it slightly more efficiently in some cases by taking a moment to think about what type of test source you might want to utilize. All right, so let's recap what we've talked about today. To find the Thevenin voltage, the process is literally exactly the same as if the circuit didn't have any dependent sources in it whatsoever. You're simply finding the open circuit voltage drop across a set of terminals for whatever case we're looking at. The Norton current process also did not change at all, right? So the Norton current is still just the current flowing through the short-circuited set of terminals of interest, okay? To find our Thevenin resistance, that process changed pretty significantly because we can no longer simply look in through our terminals and apply resistor combination techniques because there is a dependent source messing up the application of those resistor combination techniques. So we have a couple of different options. We can choose to take the ratio of V Thevenin divided by I Norton to get our Thevenin resistance, or we can apply a test source method to find our Thevenin resistance directly. Yes, ma'am. You can think of it that way, but I would argue that the resistance isn't necessarily a fixed quantity. So like if you're looking at it from this particular perspective, you would have 10 in parallel with the resistance of that dependent current source looks like 50, whatever value that thing has. Yeah, I don't know. So thinking about the resistance of an ideal source probably isn't the best idea. Just because we can measure it per se, because if we can find the voltage drop across it and the current flowing through it, the ratio of that is the resistance. Because it's not specifically a resistor, I'd kind of leave that alone, just for the intents and purposes of this course. All right, so that's what I wanted to talk about today. We've covered Thevenin and Norton equivalent circuits with dependent sources. I gave you guys the tool to analyze any of these circuits. So if I am not mistaken, there is an in-class assignment. There is also a lab for today. So that's why we only had 30-ish minutes of actual lecture material, so you can handle your other things.